When vapors ignite, the resulting flame doesn't completely burn all of the fuel, so there's smoke. Smoke is the result of incomplete combustion. There's also heat, which is caused by the rapid oxidation of the materials. And there are gases that are produced by the combustion. Gases including carbon monoxide and sulfur dioxide, to name only two. While a combination of fuel, oxygen, and heat trigger combustion, a chemical chain reaction keeps the fire going. Once vapors begin to burn, the chain reaction starts. The fire continues to produce heat, which in turn produces vapors, and in turn, the vapors fuel the flame. This chain reaction will continue until one or more of the three key ingredients are removed. Remove the fuel, remove the oxygen, remove the heat, and the fire stops. However, simply combining fuel, oxygen, and heat will not necessarily produce combustion. First, oxygen must make up at least 16% of the atmosphere for fire to burn. In some cases, 12% oxygen may be sufficient for a smoldering fire. And the heat must reach the ignition temperature of the fuel. Any substance will burn if it gets hot enough. That is, if it reaches its ignition temperature. Combine any substance with sufficient oxygen and the right amount of heat, and combustion will result. Once there's fire, there is also flame, smoke, heat, and gases, all products of the combustion. There is also a chemical chain reaction which keeps the fire burning. Fire is divided into four classes: A, B, C, and D. By classifying fires, we can be better prepared to fight them. If we know what class fire we're dealing with, we'll know what agents will best combat the fire. Class A fires include fires which occur with common combustibles such as paper and wood. Class A fires are usually extinguished by cooling. Water or portable extinguishers can be used on Class A fires. Class B fires include fires which occur with flammable and combustible liquids and gases. Smothering, cooling, or stopping the chain reaction with dry chemicals or halon are ways to combat Class B fires. Class C fires are energized electrical fires. Class C fires are usually Class A or B fires involving electrically charged equipment. So, to combat a Class C fire, you must first remove or turn off the electrical power supply, and then handle the fire as you would a Class A or Class B fire, but only if you're sure that all power is removed. If in doubt, use a non-conducting extinguishing agent. Class D fires include those which occur with combustible metals such as magnesium. Special firefighting agents such as specific types of powders must be used to combat Class D fires. With any class fire, if you remove the oxygen, fuel, or heat, or stop the chemical chain reaction, you stop the fire. Though the definition of Class B fires concerns flammable and combustible liquids, it's the vapors given off from the liquids which are the greatest concern. That's because it's the vapors given off by the substance which actually burn. This is where the term flashpoint comes in. When a substance is heated, it gives off vapors. If an ignition source is present and the vapors reach a sufficient quantity, they'll ignite. By definition, then, flash point is the temperature at which a liquid begins to release vapors. Different liquids have different flash points, an important point to understand. Flash point affects how we combat a particular fire. Consider gasoline and diesel oil. Gasoline's flash point is minus 45 degrees Fahrenheit, while diesel oil's flash point is 110 degrees Fahrenheit. Quite a significant difference. At minus 45 degrees, gasoline's flash point is easily reached year-round. This means that gasoline is constantly giving off sufficient quantities of vapors to burn. At 110 degrees, diesel oil's flash point is much higher. Consequently, diesel oil will not give off flammable vapors except in an extremely hot environment. Since we know that gasoline has a much lower flash point than diesel oil, we also know that a diesel oil fire will be easier to handle than a gasoline fire. That's because water can cool the diesel oil to below its flash point of 110 degrees Fahrenheit and stop the production of dangerous vapors. With burning gasoline, however, water cannot cool the gasoline sufficiently to stop the fire. Water freezes at 32 degrees Fahrenheit, a long way from gasoline's flash point. So even though gasoline and diesel oil fall under the same Class B category, different firefighting methods are used to combat fires involving these liquids. Besides flash point, another important term to be familiar with is flammability range, often assigned to combustible and flammable liquids. Flammability range is a specific range of vapor-air mixture which will ignite, usually listed as the lower flammable limit and the upper flammable limit. Anywhere between these limits, ignition can occur. Let's look at gasoline, which has a lower flammable limit of 1.4% and an upper flammable limit of 7.6%. If there is less than 1.4% gasoline vapors mixing with air, it's too lean. Over 7.6% gasoline vapors is too rich. Any mixture between 1.4 and 7.6 falls into gasoline's flammable range and is only missing an ignition source to burn. This is why it's so important for personnel on board ship to know the basic chemical properties of the liquid cargo it's transporting. Tank ships transporting flammable or combustible liquid cargoes in bulk have special considerations, not only because of the potential dangers involved with liquid cargo vapors, but also because rapid decision-making and action are essential in the event a fire does occur. Again, the vapors from the liquids are the primary concern. It's the vapors that burn, not the liquid. Let's consider some possible sources of ignition for a moment. On ships, ignition can come from some unforeseen sources. A two-way radio is one such source, that is, if it's not intrinsically safe. Static electricity can also provide a source of ignition. Static electricity is generated during loading and unloading operations, and if not properly grounded or bonded, can create a source of ignition. For fire or explosion to occur because of static electricity, there must be a means of static charge generation, a means of static charge accumulation, a static discharge, and an ignitable vapor. Some common accumulators of static electricity include certain clean oil distillates with low conductivity, tank cleaning machines, the moisture in steam, and oil in water spray. In review, to have fire, we must first have an ignition source. The right combination of fuel, heat, and oxygen starts the fire. A chemical chain reaction keeps it going. When there is fire, there will also be flame, smoke, heat, and toxic fire gases. Fire is divided into 4 classes: A, B, C, and D. By classifying fires, we can best decide what fire agent should be used to fight that particular fire. And for those materials which fall under Class B, special considerations must be made because of vaporization and the fact that different Class B fires may require different firefighting techniques, such as the different techniques used to fight gasoline and diesel oil fires. Most fires start out small and can usually be put out with portable extinguishers if detected early on and if proper technique is used. In this program, we're going to look at various types of portable extinguishers, their applications, and most importantly, proper technique. Technique is so important because the average 20-pound dry chemical extinguisher is designed to deliver an effective stream for only 17 seconds. A 30-pound dry chemical extinguisher represents the weight of the agent inside. This extinguisher will only deliver an effective stream of agent for approximately 25 seconds. Larger extinguishers deliver a larger flow rate, so you have more extinguishing agent but not much more duration. Also, after the initial duration of effective spray, the extinguisher may continue to spray. However, this additional spray does not contain any firefighting agent and is useless. When this occurs, you can hear the difference because the extinguisher is simply gassing itself off. This is a much hollower spraying sound than when the agent is being delivered from the extinguisher. Before we explain proper handling techniques, we first need to look at the various types of extinguishers available and their applications. We've seen that oxygen, fuel, and heat are required for ignition to occur. And a chemical chain reaction keeps a fire burning. Fires are rated into 4 classes so we can easily determine what agent to use to put the fire out. This is where extinguishers come in. Just as there are 4 classes of fire, there are 4 corresponding classes of extinguishers. Class A extinguishers are pressurized water or of the Class A rated dry chemical type. Class A extinguishers are used on Class A fires. These include fires in common combustible materials such as wood and paper. A number rating of 1A is the amount of fire that can be extinguished with 1 1/4 gallons of water. An extinguisher with a rating of 2A contains 2.5 gallons of water and is capable of putting out a fire twice the size of a 1A extinguisher. Class B extinguishers usually are of the foam or dry chemical type and are used on Class B fires, which include fires occurring with flammable gases, flammable liquids, and combustible liquids. Class B extinguishers also have a number rating which refers to the square foot surface area it will cover. For example, a 16B extinguisher will be able to extinguish a 4 by 4 foot area of burning liquid. This rating is only 40% of what an expert would be expected to extinguish with the same extinguisher. Class C extinguishers contain extinguishing agents which are non-conductors of electricity and are used on electrical fires. Class D extinguishers use dry powder and are used on specific types of burning metal such as magnesium, sodium, and phosphorus. These extinguishers essentially bury the metal and smother the fire. Class D extinguishers should only be used on the metal specified on the extinguisher. Another type of extinguisher used on type A, B, and C fires is halon. These extinguishers are typically used on fires involving electronic equipment because of the ease of cleanup and the non-corrosive nature of the agent. At the beginning of the program, we mentioned the importance of technique when fighting a fire on a vessel. Since Class B fires present the greatest danger to persons in the maritime industry, we'll concentrate on Class B extinguishers in our discussion on technique. Many extinguishers are operated by pulling a ring pin and squeezing a lever. Others may require you to remove the hose and pin. Some models require a hard rap against the top lever to become charged. Once the unit is charged, briefly test it to make sure it's working properly. Other units may require both removing the hose and physically charging the unit by hitting the top lever. And always hold the hose tightly when charging. Don't lean over the unit when charging it, since the cap might blow off, causing injury. Regardless of the charging requirement, an extinguisher should never be activated unless you're going to fight a fire. Once the seal is broken, the extinguisher must be reserviced and returned to a ready condition. Approach the fire from the upwind side of the fire. Direct the stream approximately 6 inches ahead of the flame edge, using a rapid side-to-side sweeping motion. Each sweep of the chemical stream must be slightly wider than the near edge of the fire. Advance slowly, working the fire to the back edge of the spill. Extinguish any remaining fire at the back edge of the spill by aiming directly at the flame. Do not stop your sweeping motion until the fire is extinguished. You want to corner the fire, so begin on one side of the fire and sweep the nozzle back and forth, continually pushing the leading edge of the fire away from you until it's out. Expect an average stream reach of approximately 8 to 10 feet, depending on the extinguisher. Watch closely to make sure you're actually hitting the fire with the extinguishing agent. If you run out of extinguishing agent before the fire is out, back out quickly, but never turn your back on the fire, and never stand in or advance into the product. Never stand directly over the spill as you push the fire back. The fire could easily flash back, and you could find yourself engulfed in flame. A two-person team is more effective than one person acting alone. With a two-person team, start out at a common corner, and then move to corner the fire until it's out. A four-person team can be even more effective. The main point we want to make here is that several extinguishers used at the same time can be very effective. When fighting a pressure fire, approach the fire from the upwind side of the fire. Direct the extinguishing agent at the fuel source first. Move the extinguishing agent down the stream of escaping fuel and extinguish any remaining fire by using a rapid side-to-side motion. In some cases, it may not be advisable to attempt to extinguish this type of fire until the fuel supply can be shut off. After using a dry chemical extinguisher, gas it off. Turn the extinguisher upside down. Point the nozzle skyward, and activate the handle until the extinguisher is empty. This clears the valve and hose setup, and the extinguisher is less likely to clog when refilled. Concerning CO2 extinguishers. CO2 extinguishers generate static electricity, which may be a source of ignition. CO2 extinguishers can be used on small Class A and B type fires, but are most effective on Class B and C fires in enclosed spaces. In open areas, such as on deck, CO2 extinguishers may be ineffective due to wind velocity. Remember, for extinguishers to be effective, they must be strategically located and in workable condition. The extinguisher must also be suitable for the type of fire it's used on. And the fire must be discovered early on and by someone who's ready, willing, and able to properly fight it. Water is the most readily available firefighting agent. Water cools the fire and provides a means of control. Let's look at a situation where water is used only as a means of control. Here, no agent is used to actually put out the fire. Rather, water is used to push the fire away from an open valve feeding the fire. Once the fire is away from the valve, firefighters are able to close the valve and cut off the source of fuel feeding the fire. The common use of water in this example is that of control. Of course, water does have its negative properties. It conducts electricity, so it should be used with extreme caution when fighting electrical fires, and only as a last resort, preferably after all electrical equipment has been turned off. Water reacts violently with certain chemicals, such as peroxides and carbides. It's difficult to handle in temperatures below freezing. Since water weighs 8 pounds per gallon, large amounts can cause stability problems. And if not used properly, it could serve to spread the fire if sprayed directly onto the fuel that's burning. Nevertheless, it can be effectively used against fires. As with extinguishers, technique is critical to effective hose line use. However, on hose lines, a team of 2 or more persons is called for, and as with anything else, they must work as a team. That means preparation, cooperation, and communication. And it also means having a person who serves as a leader to direct the hose line teams. Let's look at a typical team handling a hose line. The person on the nozzle controls the nozzle and the team. The nozzle should be held 1 foot in front of you, with the bail on top. The second person leans into the hose and provides major resistance to hose reaction, so the nozzle person is free to direct the nozzle. Slacking off can result in injury to the nozzle man or loss of control of the hose line. The second person must stay alert of nozzle actions and raise or lower the hose as necessary. The last person is the hose tender. The last person makes sure that there's plenty of hose and watches for kinks, tangles, and obstructions. The last person is also responsible for pulling the hose line back. When using 1.5-inch hose lines, all team members stand on the same side of the hose. With 2.5-inch hose lines, team members alternate on both sides of the hose. Each person is 1 arm's length from the other. The person on the nozzle controls the stream flow, straight stream, full fog, or shutdown. When moving in any direction, use a technique called the firefighter's shuffle. Move a step at a time in unison. One person, usually the person on the nozzle, shouts out commands to move the team. To direct the nozzle to the left, the nozzleman pivots and the hose team moves to the right. To direct the nozzle toward the right, the nozzleman pivots and the hose team moves to the left. When the fire is out, or if you are unable to control it, back out together. The person on the nozzle shouts, "Prepare to back out." This is the command that tells the last person on the hose to drop back 10 to 20 feet. This distance may vary depending on the situation. When the nozzleman shouts, "Prepare to back out," the last man shouts to the person in front of him and says, "I'm dropping back," and drops back, picks up the hose, allowing it to drag on the deck between him and the other team members. The last person pulling the hose must make sure the hose winds in an S pattern, not in a loop. This ensures that the hose doesn't kink should the team need to move forward again. When the back out command is given, it usually means that all hose teams will retreat together. However, this may not always be the case. There may be situations where one team is in front of the other, or one team may be left behind for cooling. Each situation is different. Listen for commands. We've just seen a typical hose team using a 2.5-inch line. Let's look at a team using a 1.5-inch line. 1.5-inch hose lines require less manpower and they're easier to use. Generally speaking, one person can handle a 1.5-inch line if it remains stationary. However, a team of at least 2 persons is required if the hose line must be moved around, which is generally the case. In any case, the nozzleman always controls the nozzle and gives the commands. Applicators, which spray only in a flat fog pattern, are usually available on board ship. They can be quite effective as support devices. There are 3 sizes of applicators. The 4-foot and 10-foot applicators are used with 1.5-inch nozzles. The 12-foot applicator is used with the 2.5-inch nozzle. The 4-foot applicator is used on interior fires. The 10 and 12-foot applicators are used on weather decks. Applicators generally are used for protection only. Nozzles in full fog are used to extinguish the fire. Sometimes a technique called goosenecking is used. This requires the nozzleman to raise the hose at arm's length above the head. The nozzle is brought down to shoulder level, and the nozzleman then uses a sweeping pattern in front of the hose team. The nozzle must always be on full fog whenever goosenecking. Teamwork and technique are critical to turning a threatening situation into a minor misfortune. Even with zero visibility, it's possible to battle a raging blaze as long as you don't panic and continue to work as a team. Foam is an effective firefighting agent. In this program, we're going to take a look at foam, how it works, its applications, and how to handle it when fighting fires. Foam is designed to be used primarily on Class B fires, those involving flammable and combustible liquids. When these types of fire occur, it's actually the vapors above the liquid which are burning. Foam acts to extinguish the fire and keep it from reigniting because it forms a protective layer above the liquid. There are many types of foam concentrate, normally marked as a percentage between 1% and 12%. The percentage number refers to the percent of foam concentrate to water. Thus, 3% foam is a mixture of 3% foam to 97% water. Because of the many different types of foams on the market today, you should always consult the manufacturer's specifications for correct application and use. For our purposes, we'll concentrate not so much on the type of foam used, but the techniques involved in its application. There are 2 types of foam systems: portable and fixed. Proportioners inside the portable or fixed lines mix water with the foam concentrate. Some portable units use a special inline proportioner placed in the hose line before the nozzle. Foam and water are mixed in the proportioner and sent through the hose to the nozzle, where air is injected into the spray. The inline proportioner must be compatible with the nozzle. A nozzle that delivers 95 gallons of water per minute must be matched with a proportioner rated at 95 gallons per minute. Some inline proportioners have a bypass valve built into the system, which allows the operator to switch from foam to water and vice versa. On other portable units, the proportioner is built right into the nozzle, so the nozzle mixes water, foam, and air all at the same time. These types of portable units do not get the foam supply through the hose line. Rather, portable buckets supply the foam, which is picked up through a small hose leading to the nozzle. On a typical hose line team, the last person takes on the responsibility of maintaining the foam bucket. As with the plain water line, the first person mans the nozzle, and the second person keeps the hose from getting out of control. Fixed systems usually require less manpower. On some ships, fixed foam systems may be of the balanced pressure proportioning type, which allows the foam pump discharge pressure to provide proper proportioning over a wide range of flow demands. In most cases, several valves must be opened and the pump started for the foam system to operate. Since time is so critical in a fire emergency, pre-planning is essential, and every person on the team must know his role. During a fire, the foam should be gently applied on top of the fire. If possible, direct the foam at a wall or other braking device, allowing the foam to gently roll back over the fire. Avoid aiming the foam directly into the liquid. This will only splash the fire and make matters worse. Once enough foam is applied, it'll form a protective blanket and stop the fire. And remember, water tends to destroy the foam blanket. If cooling or protection of other areas is necessary, use a fog pattern or attempt to knock down the fire and do structural cooling with straight or broken streams before foam is applied. If cooling is required after foam is applied, use a fog pattern and be careful not to disturb the foam blanket. So far in this series, we've looked at a number of different fire situations along with proper techniques for combating them. For the most part, these have involved exterior fires. In Part 5 of this series, our attention turns to interior firefighting and the specialized tactics used when fighting interior fires. There are 3 stages of burning with interior fires: incipient, free burning, and smoldering. And there are 2 basic methods of interior firefighting: direct and indirect. The incipient or beginning stage is characterized by the presence of a small localized fire. Here, the direct method of firefighting is used. That is, using a hose line, you shoot short, straight bursts of water directly into the fire until it's completely out. Once all visible fire is extinguished, move in and perform a procedure called overhauling. Overhauling involves a thorough search for any remaining embers which could cause a reignition. The free burning stage of fire is hotter, usually between 1,000 and 1,300 degrees Fahrenheit, and calls for the indirect method. Here, large amounts of heat and smoke have already accumulated near the overhead, and using direct bursts of water will just serve to scatter heat, fire, and smoke, making it very difficult to fight the fire. Visibility is also critical to interior firefighting, which is why the indirect method is used. It also leads us to the term thermal balance. Consider a fire burning inside a room. As the fire progresses, heat and smoke rise to the overhead area. Smoke, of course, is just material which has not burned, incomplete combustion. As the heat rises, it carries the smoke with it. As the heat buildup continues, it covers more and more of the upper part of the room. Cooler air with more oxygen remains down low. This is thermal balance. Heat and smoke at the top. Cooler, less toxic air down low. The longer the fire burns, the hotter and more toxic the atmosphere becomes. If the fire burns long enough, the heat and smoke will take over the entire room. If the direct method of firefighting were to be used in this stage, it would serve only to scatter the smoke and heat, as well as the material fueling the fire. Visibility can become so impaired that the actual fire may be impossible to see. This is why the indirect method is so valuable. As you enter the room, aim the nozzle toward the overhead, where the heat and smoke are. Use a straight stream pattern in 1 or 2 short blasts. The water immediately absorbs great amounts of heat, producing steam, which in turn smothers most or all of the flames. When flames can no longer be seen, straight, short bursts of water can be used to extinguish any remaining or smoldering fire. Once all visible fire is out, move in and overhaul the area. Venting the room can be accomplished by aiming the nozzle outward through a porthole or doorway. Put the nozzle on full fog and adjust it to fit the opening. Heat and smoke will quickly vent out the opening, clearing the room. The general strategy when fighting an interior fire is to discover it early, sound the alarm and gather forces, confine the fire by establishing boundaries, use proper protective equipment. So, on small fires, those in the incipient phase of burning, the direct method of firefighting is used. With the free burning phase, the indirect method is used first, followed by the direct method, using as little water as possible. And of course, overhaul the area for any hidden fire. The third phase of interior fires, smoldering, also involves high levels of heat. If an adequate amount of oxygen becomes unavailable during the free burning stage, the fire will proceed into the hot smoldering stage. At this point, oxygen content is reduced below 15%, producing high concentrations of carbon monoxide. This is a particularly dangerous situation because of the possibility of a backdraft occurring. Backdraft is the explosion or rapid burning of carbon monoxide that has been heated above its ignition temperature. This occurs when oxygen is suddenly introduced into the space. If you see smoke breathing around a doorway, where the smoke comes out of the cracks, stops, and comes out of the cracks again, You have a fire in the smoldering stage. Another indication is a door that's hot from top to bottom. What's happening is that the fire is alternately sucking in oxygen from the outside, burning it up, and smoldering again. Smoldering creates a vacuum in the room, pulling in oxygen from the outside. Incoming oxygen accelerates combustion, which builds up pressure in the room, forcing smoke out of the room. Once the oxygen is burned up, smoldering again creates a vacuum, continuing the cycle. If you open a door at this stage, you feed the fire oxygen, which is the last thing you want to do. Cooling with water is the first way to combat a smoldering fire. If you suspect the room is very hot, for example, if the door is extremely hot, don't open it. Cool it down with water until you can open it, slightly. Just enough to get the nozzle inside. Spray several short straight stream bursts toward the overhead and shut the door. A word of caution when opening the door. Don't stand directly in front of the opening, and wear proper protective equipment. When fighting interior fires, you'll need to wear self-contained breathing apparatus. Be aware of some precautions. Make sure the apparatus fits properly. If you have a beard or long sideburns, you won't get a proper seal. If you're attempting to rescue someone, don't share your SCBA. And remember, rescue is a team effort. Never go in alone. One other type of fire that requires special consideration is the galley fire. Here, burning grease is often involved. Water should not be used to extinguish a grease fire. Water entering the hot grease will change to steam, expanding and expelling the grease rapidly, thus spreading the fire. The use of a dry chemical or CO2 extinguisher is recommended. And once again, technique is important. Care must be taken not to spread the burning grease with the pressure from the extinguisher. Approach the fire down low and stay low where the cooler air is. Again, you probably only have about 17 seconds worth of extinguishing agent, so a direct sweeping motion is most effective. If other methods fail, all personnel may be evacuated from the area, so a fixed, closed system such as halon or CO2 can be used. Remember, all fires should be considered dangerous. Pre-planning is the key to most successful fire suppression strategies. And finally, work as a team. Good planning and practice will prove invaluable in an emergency.